So I'd like to welcome Bernard Caspigolet from Catalonia, from the University of Barcelona. He is affiliated with the holomorphic dynamics group there, and he was a consultant at Wolfram Research and worked closely with a few mathematicians, including Tor Taylor, who you may know from St. Francis. So let's welcome Bernard.
Thank you, József, for this introduction. So today I'm going to be talking about this notion of complex tree that I've been working for the past 2 years when I quit Wolfram to start working with this group at the University of Barcelona. I would like to start with this diagram that's like the roots of polynomials with coefficients 1 and -1 up to degree 23 that I plotted in Mathematica. So what you get is a picture like that, which is bounded in the disk of radius 2. And I find it as a metaphor also for this quote from William Thurston: mathematics is a process of starting hard enough at the fog of confusion to eventually break through to improve clarity. I took this quote from Thurston from his profile at Math Overflow. He was a big user of that platform. And there he was posting questions like this one, which made it eventually to a paper, the last paper of him, about the entropy in dimension 1, which was about the core entropy of Julia sets in the real line of the Mandelbrot set. But that's like a different story. The thing is that 6 years ago, when he was doing that, I was at Heidelberg University and I was playing with these fractal trees. I was making an interactive website using the computational document format of Wolfram. And one of the families for binary trees, when you have like one branch and then the other one is like opposite, 180 degrees, and then you're looking at the parameters where the leaves, the canopy, it's connected. And for the ones that are connected, then this is part of the set. And actually this set matches the one that Thurston was studying for the unit disk. And now, like I was seeing like 2 years ago, that the mathematical community in holomorphic dynamics was taking some interest about these sets because of William Thurston. But these sets have been studied like Kevin Head or other people for like the past 30 years. But there is a recent paper with Sarah Koch and Danny Caligari and Alden Walker about the set of connectivity for this family of self-similar sets, where they proved actually that there is infinitely many holes close to the boundary of this set, where the limit set that you get is a Cantor like in the space, it's disconnected. So I joined this group there to have more tools, and the motivation to pay attention to my talk and understand the fractals is that now I have a better understanding of the internal structure of these sets, and that's using this notion of a complex tree. So the basic idea is that you start with the geometric series. The visual representation of the geometric series is that each summon is making this n-ary tree. It's like you want a spiral thing. But then what happens if you take like several complex numbers with modulus smaller than 1? And for example, C1, C2, C3 are these complex numbers in there. So you just like start playing with the combinatorial possibilities of that. Like for example, you take like C1, C2, C2, or like C2 and then C1. That's this term in there, and you have to think that actually, because of complex numbers, the multiplication is commutative. You have that actually these vectors are they have the same length and then the same direction, and then there is these other ones in there. But the idea is that when you start like doing that, you end up with limiting points of a self-similar set, and that's another example for these two values. You get a binary complex tree with 2 complex numbers. So the idea is that you want all of the branches to be contractive, like the modulus to be smaller than 1. You get an alphabet, and then the alphabet is encoded by the symbolic numbers, which have a complex value associated to it. Like 1, it's going to be C1, and in this case, this example, it's for this complex number, and then C2. In 2, like it's this other complex number in there. So that's like you're going to take the letters from this alphabet, and then from that, with these letters, you're going to construct a word, and then this word is projected by what I call the geometric map, phi. And as an example, for example, 2 is just like 1 plus C2. Phi1 is just 1 plus C1, and then 1, 1 is like the geometric series style. But then, for example, 1, 1, 2 is this node in there of the tree. And the way that you have to think about is that you take your word, and then you multiply the terms, like C1 by C1 by C2, and that's this little vector there. And then you chop like you remove the last letter, and then you have to multiply it again, like C1 by C1. That's this vector in there. And then you have to chop it again, and then that's C1. And then you chop it again, you end up with the empty string, and the empty string is always mapped at the root of the tree for all the n-ary trees. Now you can like think about what happens when you have an infinite sequence of letters. When it's finite, I call it all these points nodes of the tree. And if it's infinite, then I call it tip points of your like complex tree. An example is like the geometric series. That's this dot in there. You can also have it for the C2 value. So that's the other one. And you see that you get a closed form. And then for example, if you take like C1, C2, like 1, 2, 1, 2, you end up with this expression that also have a closed form. So if your word is periodic or eventually periodic, you can have a closed form as an expression. So when you remove or you take only like the tip points, what you have is like the Self-similar set, that's obvious. Here I'm calling the ones that are starting with the 2, and the ones starting with 1 are colored in black. And that satisfies the Hutchinson equation, self-similarity. And the maps that you are dealing with this is an EFS of these two very simple linear maps. And what, for example, F2 is doing to your whole tip set is just like scaling down by the modulus of C2, and then adding a rotation for the argument of this complex number, minus 31. And in this case, I add this translation by 1. So that's you can do the same for the F1, but in this case, rotating 63 degrees. And after applying these two functions, you end up with the same result. That's like the invariant set. That's very introductory, but I call these first level pieces F1 and F2 in red. Because of self-similarity, if you can prove that these two pieces are not intersecting, then the whole tip set is going to be a Cantor-like one. So the key idea I had here is to have this tip-to-tip gluing condition, and then I was imposing these two points to be connected. This pair of tip points have to be connected, and that's when you get these closed forms for this tip point, and then for the other ones as well. So here I'm imposing that they have to be equal. They have to join, and these other ones they have to join as well. So you have a system of two equations with 3 complex unknown variables, which actually it gets reduced in Mathematica by this parameterization of the C1, the branch, the black branch has to be your parameter Z, and then C2 has to be always constant at 1/2 plus 1, and then C3 has to be a Mobius transformation of the C1 1/4. So now with this. We just like obtained a family of ternary complex trees that are parameterized in this way, and if we keep this structure, then we know that at least the connectivity of the tip set, the tractor, is going to be connected in these 2 points. It can happen that you have more than one of these, but for this value there, you have only 2, and these 2, for the intersection of the piece F1 with the F2 is this point D that happens right there, and then for the F3 in blue and the red one, you get this other point E. So you have these 2 pair of tip-to-tip equivalence relations, and that's what I call the topological set of your self-similar set. And that's for this value that you have this condition in there. But so I was saying that I was calling them this kind of trees that are structurally stable, in the sense that you can perturbate the value that you are starting with, and then and notice that you are still like having only 2 points of contact, and that's what I call a structurally stable tree. And the family that we have, it's defined for this parameter space where it's contained in this annulus, because you want the branch C3, in order to be smaller than 1, you have to have C1 to be bigger than 1/4. So the family is defined in this anomalous from 1/4 to 1. That's the perimeter space, and the example I was showing you is this point in white. And now I'm just gonna take different values of these values. You see that the geometry is starting to change, but the topology still keeps being the same. The topological set doesn't change. I'm just gonna move a bit right, like left upper right. So and then you get this dot in there, because now you have an extra connectivity within the F1 and F3 in blue, and that's when your topological set has changed. And when that happens, I call the perimeter point as black. The way I'm computing like new dots is just by imposing extra tip-to-tip connectivity conditions. For example, this expression there, it gives you this algebraic expression in terms of your parametric alphabet. And then this other tip point is this other expression in there. And actually, this is like finding the roots of a certain polynomial. And if you solve it, you obtain this number there, and that's encoding these 3. And for the other ones, you have the same. So like this is like 1, 1, 1, 2. So it's 1, 1, 2, and then going to the middle. And actually, it's meeting these other branch paths, like 2, and then 1, 1, and then 2. So you get this polynomial, you solve it, and then you have this is the square root of 7, and that's giving you this element. And the same for the other one. So you start like plotting these dots. And I was crunching many solutions with Mathematica, and what you get is this map up to the degree like words of the length 13, and then appending the 2, 2, 2, 2 equation. And the white region in there is where you have a structurally stable trees. And these 2 dots correspond to the Sierpinski triangle, and actually prove that it's piecewise smooth, this set. The boundary where you have to just touching pieces, but when you move away, it's gonna have overlaps, and so it's made up of like 2 straight lines. Here it's a Sierpinski triangle when you start like moving down in this part, and then you have to switch to this algebraic curve this way, and then there is a critical point that you have to move again at -1/8. 1/8. You have to switch to this algebraic curve in there. So I'm going to show you an animation starting with the Sierpinski triangle that goes down and then switches and goes back to this point. And here you see the pieces just touching and then rotating. There is a critical point. We're going through here. And it's just like evolving a bit more. Now when you get this piece intersecting, it's that, and then like sliding a bit more until you get these tangential intersections, and that's when you are going up around this set. So the way to prove it, I'm not going to explain it here, but it's available in my master thesis. I defined it 1 year ago. It's very simple in the sense that this family is made up of straight lines in the outer boundary, and that's why when you get these algebraic curves in there. So another thing that you have to see is that I was proving only this part because actually only half of the anomalous is necessary to prove it. In the sense that when you are like sliding the black branch C2, C1, then the C3 is actually moving the reverse way. So you were moving here, and then the other one is moving upwards in this region. So there is this Mobius transformation that simplifies. There is this extra symmetry in there. So you can see that now we're moving the branch in there, and like the blue one is like going through this part in there, and C2 is always constant 1/2. So this tip point there is always like pointing at 2 in the space, and then you see these symmetries of the partition of the anomalous in this case. So it's interesting to find these critical points when you have some algebraic numbers that pop out, and also right in the boundary and in the interior part, you have that the similarity dimension matches the Hausdorff dimension. And actually, it's interesting to study the dendritic structures in the interior, where you have topologically homomorphic self-similar sets, and then apply analysis on them, and then find some optimal conditions. And there is the maximal, like the higher Hausdorff dimension that matches the similarity dimension is found in this part in there. There is two maximal points. Another concept is what I call the root connected trees. And that's why when you have that there is like a tip point that lands at 0. If that happens, then automatically you have that your tree is connected at 1, in the sense that the 3 level pieces are intersecting at 1 when you just remove one. So like, and out of that, I was like finding like a subset of this connectivity, like the unstable set M, and that's this map that you have there. Actually, this is a subset of the other one, because for the initial conditions, we didn't have any kind of the tip point that went to 0. But when you are overlapping, then you can have some critical points. So like this one is found in there, where you have this 1, 1, and then always 2 that meets at 0. And then for this other one, it's also like you're going this way, and then it ends up at this dot that's 0. So natural question was to ask what happens if you get this map when you try to figure out which trees are getting you a point at 0. Then if you change this lambda value for these equations, instead of 0, you take like 1, for example. And because I had this theorem that tells you that 1 is going to be also contained, it's going to look exactly the same. But now, if instead of using 0 or 1, you use other parameters, and in this case, I was using lambda different from 0 or 1, and I'm going to show you the animation going through this point up to the cycle, and I'm switching the real axis to the imaginary one, but that's what you get, more or less, after it. And it's interesting because you get this asymptotic similarity when you get close to the points. So you take an element, it's going to look like what are you seeing right there. This critical moment when they touch, it's when you have the Sierpinski triangle. So that was just one example, one family, but you can construct, for example, taking -2, you have these 2 pair of branch paths, and using the same logic, you have a system of 3 equations of 2 equations with 3 unknown complex variables, which actually get reduced, and it's very similar to the other one, but only what has changed is just this value, -1/2. And in this case, you get a not piecewise smooth boundary. Now it's rough, and there is one piece that it is smooth. That's one of the parts I'm working on to show. But here you also get some Lambert points where algebraic numbers pop out. But in the interior, they are connected, but they are just like simply connected in the sense that you can access them, and there are no holes for it. So that's another example in there. And why we had before piecewise smooth boundary is because fractals are rough in general, and when you're trying to collide the first level pieces, you have a lot of ins and outs, so you have to switch it and find a lot of equations. But for this family with the Sierpinski triangle, the external boundary is made up of straight lines. So when you're colliding the different pieces, then this is just like getting you algebraic curves, because it's just like a sliding. For example, this piece is like a sliding around this edge in the blue part until you get the critical point, and then you have to switch to another algebraic curves. I was happy to find that these 2 elements are used as logos, and now we have a family related to them, and this is like the logo of the students of the Canadian. So yeah, and then the ARMS is also having this logo with the reverse of the Sierpinski. So that was an interesting, funny thing to share. For one half, when you're moving the parameters at 1/2, you get mirror symmetric ternary trees, and that's the type of systems I was studying 6 years ago. But now, with this notion of complex tree, I'm able to break down this mirror symmetry. I can just move this way, and then this branch is going to be shrinking. That's the 1/4 map, the Mobius transformation. So you have to think that each piece I was defining 6 years ago, now you have a region like that where you can explore it, and all of them are going to be topologically homomorphic. So getting back to this map that I was showing you before, in this white region, you get Cantor-like disconnected trees. And I was taking one in the boundary as the typical H3 thing. But I was also constructing this map. So for the unit, this is where you have all your trees. And let's zoom in, and I'm taking just one element for this big dot. And the size of the dots are giving you are telling you that the degree of the polynomial that you are like solving, and like this is like the root of a polynomial of the degree 3. It has some like this is also a degree 3 polynomial, and from this one you get this binary complex tree, and this is actually telling you the length of the word when they're like meeting from the other, starting with a 1 and starting with a 0. And it's like it's a visual representation of the actual root, and in this case you get a Rauzy classical fractal, and the intersection is just by intersecting the two pieces, the first level two pieces, you get the whole tip set and plus like two fractal curves. So actually, like when you try to pull apart this piece-to-piece overlap, the first like solutions are going to be polynomials of the higher degree. And yeah, so that's like the intersection between the first level pieces. And here you can like play with the collage theorem, and then actually like the branch paths, it's important in the sense that this is going to tell you like the function. So like in here it's like 2, and then it's black, so it's 1, and then 2. And that's like this piece in there. So that's like the function f2, 1, 1, 2. And then you have these other pieces. It's like 1 and then 2, 2, 2. That's this piece in blue. And the same, like the branch path is telling you how to define your functions in there. So it's 1 and then 2, 2. That's this piece in there. And that's going to be giving you this a fractal curve that defines the boundary of this overlapping tree that's found as a root of a polynomial. So and why I'm like having these like tree structures that maps this map that it's related to the first one is that I'm having like hierarchical solutions. So in this case, these are like the roots of the different polynomials. And for the degree 3, you had the one that's related to the Rauzy fractal. But then the next step is like matching it, and then I'm joining these two roots together, and that's like having just a branch path in there. So you can keep like branching, and then in this case, I'm just like showing the ones that are giving me some solution that goes to the boundary. And like for like if you remove, for example, some terms where you include 0 as coefficients, you can have like other families. In this case, I'm removing the coefficient 2, and then from here, that's like the other green dot. You actually go down, and then you also get to the boundary with a shape like that. And this corresponds to this red part. So I'm having separated families for each one, depending on the way they are connected in the node-to-node connectivity. And that's for the red part. So you start like overlapping all these structures, and then you end up with a map for the connectivity. So that's why I think it's a better way to look at the interior part of these sets. William Thurston was well aware with the relation with Selzheimer sets, and the map key was defining the master teapot, that's now called. And another tool that you can do with, for example, elements in the boundary is, for example, in this case, you have just touching pieces, and you have like two pair of relations. So you can like take one relation, and this tip-to-tip equivalent relation is going to give you a family, and for the lower part, it's going to give you a different family. And that's for the upper part, and that's like the perimeter space where your family is defined. You can see that you can have overlaps, but at least there is one connectivity condition in there. So this is like the parameter Z, and the other branch is going to go around this algebraic expression. So, and then for the lower part, you have another family of this branch. So you can think about these two families having some elements in common. And in this case, we have one element that's in there. That's the one I was showing at the beginning as an example from the boundary. But then you can also find that there is another example that actually have this condition, and actually it's giving you a Selzheimer set that's tiling the plane. It's a kind of like Rauzy thing. So I will stop here. Thank you very much. And I would also like to thank the organizers, and especially József that contacted me and invited me here. Yeah, so thank you.